And finally, we're going to take a look at exponential models. Exponential models have the following characteristics. In a table of values, the growth or decay factors are equal. The graph represents an exponential curve. And notice we have exponential growth. It keeps on increasing from left to right. And exponential decay. The graph decreases from left to right. The equation of an exponential model can be written in the form y equals a times b to the exponent x, where a is the initial value and b is the growth or decay factor. So let's go to example 1. Which models represent an exponential relation? Since x is in our exponent for the first one, we can consider that relationship an exponential relationship. Notice in our second one, x is not in the exponent, and since the exponent is equal to 2, this is a quadratic relation. So let's look at our two graphs. You see the first one is a parabola, so it's not exponential. Again, that's quadratic. In the second one, it could be an exponential equation since it's always increasing. Finally, let's look at some tables. So remember to check to see what type of relationship we have. We're going to look for the average rate of change. And recall that's taking the delta y's and dividing them by the delta x's. So 25 minus 35 over 2 minus 0, which gives us negative 5. Same thing here. 20 minus 25 over 3 minus 2, that gives us negative 5. And if you try the third one, you should also get negative 5. So since the AROC is constant, this is a linear relationship and therefore not exponential. Next table, we're going to find the average rate of change again. So 64 minus 51.2 over 2 minus 0. And if you try that one, you should get 6.4. Then go to the next one. It is 80 minus 64 over 4 minus 2. And for this one, you should end up with 8.0. And finally, the last one is equal to 10. Now you see these are not increasing by the same amount, so they're not quadratic. However, if you take the ratio of the two numbers, so if you take 8 and divide it by 6.4, we end up getting 1.25. And then you do the same thing here, 10 divided by 8, we also get 1.25. So you can see that these numbers are all being multiplied by 1.25. And that is what we call the growth factor. So they're increasing by a factor of 1.25. So therefore this is exponential. Example 2. Determine the exponential relation y equals a times b to the exponent x that best fits the data in this table. And keynote, where x is the number of years since 1921 and y is the population of British Columbia in millions. So before we plot this data, we need to determine the value of x. So here's our x, here's our y. Years since 1921, so 1921 would be 0. 1931 would be 10 years later, then 20, then 30, 40, 50, 60, 70, and 80. So we are going to graph these values for x and these values for our y. So we're going to use Desmos, and as shown here, we end up with the following results. But let's go to Desmos now and try this ourselves. Here are the table of values now added into Desmos. The next thing is to label our axes. Now we want to add the curve of best fit. So we're going to add an exponential curve of best fit. So recall that we're going to start with y subscript 1, because that's from our data set. Use our right arrow. Use our approximate symbol. And then a, b to the exponent of x. And remember, that's x subscript 1. And then hit enter. There's our a value, our initial value, 0.6038, and our growth factor, 1.02466. So let's go back to our note. Our equation of best fit is y equals 0.603816 times 1.02466 to the exponent of x. What do our variables represent? Well, recall the x is the years since 1921, and y represents the population in millions. Part C. What do the values of a and b represent in this situation? So a is what we call our initial value, so that's our initial population, or it's the population in 1921, predicted by this model. And b represents the growth factor, which is 1.2466, which means that the population is approximately growing at a rate of 2.5%, the 2466. Estimate the population of British Columbia in 1985. So first of all, we got to figure out how many years that is. X is going to be 1985 minus 1921. And therefore x equals 64. So we have two options. We could sub it into our equation, or we can go to Desmos and sub in the number 64. So we want an x value equal to 64. Then if we click on the point, we see it gives us 2.871. So 2.871 million people in 1985. When will the population reach 6 million? So this time we're given the y value. We're saying that y is equal to 6, and we need to find the x value. So again, going back to Desmos, we have y equals 6. There's the line up there. We click on that, and ends up being approximately 94.263 years since 1921 will give us 6 million. So therefore the population will reach 6 million in the year 2015. So 1921 plus 94. Would your prediction in part D or E be more reliable? And this is based on extrapolating or interpolating the data. So for part D, well, we made a prediction within our data values, whereas for part F or part E, we made a prediction outside of our data values. So part D would be more reliable. All right, let's summarize exponential models. So first, looking at the equation for an exponential model, it'll be of the form y equals ab to the x. Notice our exponent is now our x value. Remember, this is our initial value, and this is our growth or decay factor. And our unknown or our variable is the exponent. So for example, an equation could be y equals 3, 2 to the exponent x. For our table of values, if we were to look at the average rate of change, first of all, we know it would differ. However, we also have to look at the ratio between these numbers. So 8 divided by 4 equals 2. 16 divided by 8 equals 2. So this has a growth factor of 2. We multiply each of the A rocks by 2 to get the next average rate of change. And finally, the graphs. So if you look at the graphs, we're either going to have exponential growth, which always increases, or exponential decay, always decreasing. Again, for this homework set, there are questions which you will need decimals for, 11, 12, and 13. Good luck.